Hello, everyone. Thank you for coming to our February online lecture event. We are the Center for Climate Science and Engineering at the University of Toronto. We try to host monthly guest lectures. My name is Mohamed Julayer. I am the CSE manager. Today, we are pleased to feature Dr. Rodrigo Costa from the University of Waterloo. First of all, I'd like to go through the land acknowledgement. We wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across the Turtle Island, and we are grateful to have the opportunity to work on this land. If you are new to our guest lecture series, welcome. We are the Center for Climate Science and Engineering, which is a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, and it was established in 2019. The CSE consists of a diverse and multidisciplinary team of faculty members who collaborate on interdisciplinary research at the intersection of climate science and engineering. Our center's director is Oya Marjan, and she focuses on structural analysis. Daniel Paulson focuses on life cycle assessment. Ahmed Ibrahim works on hydrologic variability and processes. Karen Smith focuses on atmospheric science. Mohammed Bashir focuses on hydrology and water resource systems. Paul Kushner looks at climate dynamics. Sam Markov from the University of California, Merced focuses on sustainability and resilience. And then me, the CSE manager. So one of the primary initiatives undertaken by the CSE focuses on providing education in climate science and engineering. We have developed and launched 3 graduate level courses at the University of Toronto. Additionally, we have created 8 online learning modules that are now accessible for use across higher education institutions in Ontario. We also design and run 2 courses through University of Toronto's Deep Summer Academy for high school students. Furthermore, our faculty members are engaged in collaborative research projects at the intersection of climate science and engineering. Also, our team organizes outreach activities just like this one, where we invite public and university community to give a presentation on topics that are aligned with the mandate and vision we have at this center. Now, I'd like to introduce today's guest lecture speaker. Dr. Rodrigo Costa is an assistant professor in the Department of Systems Design Engineering at the University of Waterloo. Dr. Costa's research looks at how physical, economic, and social systems in communities interact to create disaster risk and worsen socioeconomic inequalities. His work focuses on developing high-fidelity, high-detail regional risk models to simulate the impact of disasters on urban areas. Dr. Costa is also a co-lead researcher on 2 important projects: the Center of Excellence in Climate Resilience and Equitable Housing, funded by U.S. Department of Housing and Urban Development, and the Retreat from Risk project supported by the New Frontiers and Research Fund International Climate Science Program. In 2021, he received the Best Graduate Award from the Earthquake Engineering Research Institute for his work on simulating the impacts of disasters on communities. Dr. Costa, welcome. We are very happy to have you here today and excited to learn more about your research. Now, the floor is yours.
Thank you for the kind introduction, Mohammed, and thank you the CSC for the invitation. So I'll go ahead and share my screen. Please let me know if you can see my slides.
Yes, we can see, and it works perfect.
All right, thank you very much. So I would like to talk to you today a little bit about some of the research I'm doing here. So I aim this presentation more for students, for you to learn a little bit about like what can we do. So my background is in civil engineering. I have all my degrees in civil engineering. But I have never been exposed to some of the topics that I work with today. A lot of them related to how can we use engineering knowledge to better understand the impact of disasters to communities and help us make better decisions. So as I go through my presentation today, I would like to invite the students we have here to think about that as well. Think about how can we use engineering knowledge to address disaster risk. So I'm going to go over a few examples of research work that I've done. I'm not going into a lot of details in terms of the methodologies. I'm more trying, it's more of a inspirational talk than a technical talk, I would say here. So my talk is about use the computational simulation. So I'm asking you, can we use computational simulations to help us with the wicked problem of disaster risk? So I think one of the first questions we have to answer here is what is even a wicked problem? But to do that, I'd like you to first ask you a question, which is, um, how many of you would know how to solve this problem here? So if I'm giving you a block of mass M, I apply it a force F. I assume most of you know a very well-known relationship that allows you to understand how the acceleration in this block will work. We have Newton laws that tell us that, right? And I imagine most of you have been trained extensively to how to solve this type of problems. So let me ask you a second question then. What if the question was now, how can you help with mitigating socioeconomic inequality in Rio? How many of you have ever considered that question, or how many of you have been trained to answer this type of question? I assume not most of you. And if you think about how these questions affect our society, I think the second question here have a much perhaps bigger implication to well-being of humans in the world, right? So my question, and I teach a course about computational modeling at Waterloo, and I ask the students, so why do they think they have been trained to solve one type of problem but not the other? Why have we extensively taught them F equals ma, but we have never asked them to think about how can they address the problem on the right? And the reason is that the problem on the left is what we call a tame problem. So a tame problem is not necessarily an easy problem. It can be quite complicated. There's a lot of very complicated problems that are tame problems, but a tame problem is one for which we know what the problem is. We know where to start. We know where we need to get to. And a lot of times we have the methodologies to get there. So because of that, it's much easier to teach students how to solve tame problems. On the other hand, the problem on the right is what is called a wicked problem. If you ask 10 different people why there is socioeconomic inequality in Rio, you're probably going to get 10 different answers. And for each one of those answers, the solution to that problem is going to also be different. So, and it's hard to think about this type of problems. It's hard to address this type of problem because in some cases, it may not have a simple solution. So, in many cases, it's even hard to define what the problem actually is. And that is the characteristic of a wicked problem. So going a little bit more on the formal definition of what a wicked problem is, there's this paper from 1973 by two professors at Berkeley, where they defined the 10 characteristics of wicked problems. They are not the first ones to come up with the idea, but they are at least acknowledged as the first to formalize the idea of a wicked problem. So according to the two professors, Rittel and Weber, a wicked problem is one that doesn't have a definite formulation. So it's even like trying to define what the problem is in itself is a problem. There's also no stopping rule. So if I asked you, when would you be satisfied with reducing inequality in either Rio or Toronto or any other city, there's no exact point where you say this is enough reduction in inequality. The third characteristics of a wicked problem is that it doesn't have solutions that are true or false. Usually you talk about solutions in terms of them being good or bad. So for many people, that's not good enough, no pun intended, because it's easier to deal with yes or no. But in many cases, for wicked problems, you're not going to have that. The fourth thing is that there's no immediate test for a solution, and there's no ultimate test for a solution. So you can test, and the solution may pass one test, but another test, it may fail. The fifth characteristic is that every wicked problem has a one-shot operation solution. So you don't get to try it again. So let's say, for example, if the 401, it can be considered a wicked problem. You cannot go there and build a new lane on the 401 just to see if it works. You have to, when you make that decision, that new lane will be built, and you have spent the budget you have, and you have to deal with the consequences of that. Number six is that a wicked problem, wicked problems have innumerable number of potential solutions. So every person you ask may have a different solution because they see the problem in a different manner. Every wicked problem is also unique in a sense that if you solved or if you have made significant progress for a wicked problem in Waterloo, if you face the same problem in Toronto, maybe that solution is not going to work. So the solutions are not transferable. The eighth thing is that every wicked problem can be seen as a symptom of another problem. So we could think about inequality being as problems in distribution of wealth. It can be a problem in distribution of opportunities or in distribution of education. The ninth thing is that whichever the choice of explanation for that problem, the way you frame the problem will dictate the resolution you come up for that problem. And the last thing is that the decision doesn't have the right to be wrong in regards to wicked problems. If you think about climate change, if we make a decision that is wrong today, 50 years from now, we're not going to be able to come back in time and say, oops, we made a mistake, so let's try something else. So if we make that mistake today, we're going to be in trouble. So over the last 60 or 70 years since this paper has been published, this have been the 10 characteristics of wicked problems that everyone has been focused on. And I believe that there's one of these alternatives that we can actually work around it. And this one is number 5, that for a wicked problem, we have to deal with these one-shot operation solutions, that we have to make the decision and deal with the consequences of that. I argue that there are tools that we have nowadays that were not available when the authors wrote the paper in 73 that we can use to test solutions in a more in a safe way in order at least to understand what the potential impacts of those solutions will be. So I think that when the authors were thinking about that problem or thinking about these characteristics of the problems, you're thinking about a situation where, let's say you are trying to come up with some alternatives or some plans to reduce the risk of earthquakes to San Francisco. At that time, the only alternative to test that would be to put San Francisco on a shake table and see what happens and see if our alternative works or not. So that was not viable at the time. However, what we can do, nowadays we can create a model that simulates that city of San Francisco in a safe computational environment. We can expose that to earthquakes and we can test alternatives. We can try different things in the safe environment and we can gain insights on whether an alternative is viable at reducing that risk or if it may have some limitations that we couldn't anticipate. So a lot of the research I do nowadays is about creating computational simulations that allows us to test potential solutions to wicked problems in a safe and costless, relatively costless environment, which is a computer, and use the information we get from the simulations to help decision makers to make better decisions. Um, it still are going to be one-shot operations, but they will be at least educated one-shot operations. So the environment where I work is this mass of disciplines that my friends and I tend to call natural hazards engineering. So if anyone has a better term for this mix of disciplines, I welcome suggestions here. But um, natural hazards engineering for us is a mix of disciplines that combine catastrophe modeling. So maybe nowadays I don't do that as much, but I used to do a lot of hazard modeling. But I still work a lot on exposure modeling, which is to understanding like what type of buildings we have in a community and how vulnerable they are to natural hazards. Understanding impacts to individuals. Back in the day, in the beginning of earthquake engineering, people used to talk about death, dollars, and downtime. I think nowadays we have a better understanding of impacts to individuals and don't look only at those immediate impact metrics. And there's also a lot of probability theory here because you have to be dealing with hazards. Hazards are inherently probabilistic. So you need a lot of that more core engineering knowledge there. But I also combine on that modeling and simulation. So specifically, I use agent-based simulation for my in my models. But you can also derive some data-driven models from data from previous disasters and understand that from there. And a lot of the problems I work at are at the community scale, entire cities, simulating entire cities or entire regions of the world. As I'm going to show, my last example today is a case study of coastal British Columbia. So you need to understand a lot about spatial analysis. Spatial correlations are a key parameter in that. But there's also a lot of no engineering topics that I need to manage on my day-to-day analysis here. So a lot of concepts from urban planning. I need to understand public policy because it's directly related to what can we do about disaster risk. You need to understand sociology, or at least the basics of it, because you need to understand, you need to read the literature on disaster impacts from previous disasters and be knowledgeable about it. So, and you also need to understand at least the basics of economics because you're going to be dealing a lot, if you're involved in this world, you're going to be involved a lot with insurance or financing of disaster recovery because financing is a big challenge for disaster recovery. So if you are interested in this mix of disciplines here, I would suggest that you look more into natural hazards engineering. So to give you a few examples of this work that I'm doing, I'm going to walk you through 3 case studies, focus on different hazards. The first one is floods, second one is fires, and the third one being earthquake. And I'm going to tell you a little bit about how these simulations can be used for us to gain a little bit of some insights on what can we do about these hazards. Like I said, I'm not going to go into the details about the hazard modeling, for example, or the agent-based modeling, but I will be happy to answer any questions that you may have about those. So my first example is about the compound effects of repeated events. So let me give you a few examples of that. So I don't know if I can see. Oh, I think I stopped sharing my screen. Um, let me- can I see? Okay, yeah, here's the chat. Can you just give me some answers? What do you think is a bigger problem? Do you think that a 100-year period storm is worse, or do you think that a 20-year return period storm is worse? And for those of you who are not familiar with this wording here, um, a 100-year return period storm is one that happens on average every 100 years, and a 20-year one is one every 20 years. So it has to do with the magnitude of that event. So do people have access to chat?
Yes, Professor.
Okay, let me see if I can see if anyone can. What do you guys think? The 100-year or the 20-year return period? Which one do you think it's more damaging? I have a 100, I have 20. So there's a bigger split than I anticipated. So if we look at one specific storm, a 100-year storm is a bigger storm, is rarer, is something that you're not going to see very frequently. So if we flip the tables a little bit, I'm going to ask you a question that has one word difference there. What do you think is a bigger problem? 100-year period storms or 20-year return period storms? So the key difference here is now I'm asking you not about one event. I'm not focusing about on the singular anymore. I'm asking you about the plural now. So how relevant does that plural is? So we asked our questions because in many cases, whenever there's a storm, if someone has significant damage to their homes, uh, especially if there is damage sufficient to actually they needed to get a large loan to repair their homes. In the US, which is where this case study is, the longest loan you can get for repairing your homes after a disaster has a maturity of 30 years. So you can get a loan that is pretty much equivalent to a mortgage, and you can pay that loan over a 30-year period. The problem is that if you are exposed to those 20-year return period storms, um, they are much more frequent. So over a period of 30 years, you're expected to experience that storm at least once. There's a probability of 0.78 that you're going to experience it at least once, or there's even a 44% chance that you're going to experience it more than once. The 100-year period storm is a larger storm. It will probably cause more damage, but the probabilities of experiencing that event are significantly smaller. So when you're thinking about not now what the damage of that storm can be, but what is on the day that the storm happens, but if you think about the long-term impacts of that storm. So imagine during the lifetime of your home, you experience a 100-year storm at some point there, and you get a loan. So you get some debt that you need to pay now because you had experienced damage, your house flooded. You had some debt. So you have to manage that debt now. And if you're not insured, you may have to rely on a loan to pay for that. So the 100-year storms are more likely to be spaced out in time to the point that you might be able to have paid the initial loan before you experience the next storm. So if you look at those 30-year loans there, but the 20-year return period storm, especially if you start accounting for impacts of climate change and looking at long-term impacts, how it can impact sea level rise, those storms are more frequent. And it is possible that you're going to experience one before you finish paying the loan that you got to manage the impacts of the first one. So you start having this compound effect of these storms. One other aspect about this large versus big storms is that usually when we have a major event, there are some federal government assistance that can be triggered. And that can be quite helpful to help people with post-disaster recovery. In Canada, we have the DFAA, the Disaster Financial Assistance Arrangements, that they just released a new version of the DFAA last week, I believe. I need to update my knowledge on the DFAs, but I still believe that the per capita losses that are experienced within a community dictate how much cost sharing the federal government has with the provinces. And in the US, the federal government will only provide assistance to a community if there is a minimum threshold of losses. So those small storms are much less likely to receive external assistance as well. So they happen more frequently, and you have less assistance to deal with. We're more like you're on your own for those storms. So we did a study looking at the long-term impacts of floods in East Palo Alto. So we selected East Palo Alto because it's a city in the Bay Area that was some of us were living pretty close to it at the time. So for this case study, we looked at a lot of things. We look at comparing 20 years versus 100-year storms. We compared the impact of sea level rise as well. We looked into a few different things, but here is the city that we looked at. So it's subject to coastal flooding in the community. And here's the probability of experiencing at least one flooding event in the next up until 2050. So in this project, what we are looking is potential consumption losses. So imagine before a disaster, you have a baseline amount of consumption. You can think about this: how much money you spend at groceries, or how much savings you're able to put aside on a given year, how many trips you take on a given year. But we're considering here you have that baseline availability of that baseline consumption, but a disaster reduces that consumption. And during the time you are paying back a loan that you have to get to recover, to pay for the cost of repairing your home, your consumption is reduced. So of course, here's I'm exaggerating here, but that reduction in consumption may mean that you're going to take one last trip at the end of the year, or maybe you're going to have to delay your retirement because you're not able to save as much, or you're going to have to, instead of sending your kids to the best school they can, you're going to have to send them to the local school. So there can be a lot of impacts from this reduction in consumption here. So this is how we estimate, how we translate that change in consumption to an impact that we call it well-being losses, or you can think about that in average consumption losses that we have. But it's basically just looking at the differences between your pre-disaster consumption and your post-disaster consumption and integrating that over time. So for the complete study, we looked at two events, two different dates, two levels of hazards, three different scenarios in terms of federal government assistance, and we look across four economic income groups here. I'm only going to show two sets of results that kind of summarize the message from this study. So here on the left, I have some of the results we got for the 20-year storms, and in red, the 100-year storms. So what we're looking here is the debt that, so we ran a lot of simulations. So on average, this is what we get. So this is the yearly average debt that a household with very low income, and very low income means less than 50% of the median income of the region. So we looked at what is the expected loss of consumption for these households due specifically to these two types of storms here. So by 2050. So what we, and on the right-hand side, we have the same results, but now looking at the high-income households. So first, comparing the two storms. So the 100-year storm is expected that on average, it will cause a consumption of loss of 1.6%. So this is equivalent to saying that these storms are expected to cause you to have 1.6% less income available to you. And when you look at the 20-year storms, the 20-year storms have basically more than twice as much impact because of that compound effect of those storms. And on the plot on the right, we have the same results for the high income, on average for high income households. We can see that the 20-year storm still causes more consumption losses, but overall the consumption losses are smaller because higher income households, they don't need to get into debt a lot of times to pay for the potential impacts of these floods. So just as an idea to compare here, what this 4% means, so the year-over-year changes in private sector nominal average hourly earnings in California before 2020, it's hard because the pandemic changes a lot of things, were between 2 and 4%. So the bottom line here was that this 20-year storms are expected to basically neutralize wage gains for lower income families in the region by 2050 if nothing is done about that. So in the paper, we explore a few scenarios where there's some changes in how that federal funding is, how likely it is for that federal funding to be available to some communities, which is the results in the bottom here. You can see that instead of now these low-income families having a reduction in consumption of 4%, that reduces to 1.7%. And the reduction for the high-income households is basically negligible because they don't benefit as much from having that federal assistance available to them. So this here is just, I'm not going to go into a lot of details in each one of these plots, but just to show how we can use some computational simulations to understand what the potential long-term impacts of disasters are, and then comparing across these potential scenarios of what can we do better and who would benefit from this improvements in how that federal funding is allocated. Now I'm going to move to a case study where we're using some simulations to understand, again, post-disaster financial aid, but in a case of scenario of a wildfire. So here I have some images from the California fires. I think many of you have seen these images in the news quite recently. Um, but the images you may have seen were similar to these ones, but not these ones, because these ones are actually from 2017. So California is a place that we have enormous wildfire risk, so much so that it's difficult for some families to get insurance because the locations where they live, it's prone to being affected by wildfires. There is a lot of things in California. There's like the vegetation is quite prone to wildfires. It's an area that where it rains just a few months of the year, so they have a major wildfire risk. So in 2017, the Tubbs fires affected the cities of Sonoma and many townships in the city of Santa Rosa and many townships in the county of Sonoma. And what happens after those fires is that the fires happened in October 2017, and there's a subsequent fires in other part of the state in December 2017. So when there are large disasters like this, as I was mentioning, there are some potential for aid coming from the federal government in the U.S. So let me walk you through the timeline for that aid. So in April 2018, maybe like 4 months after the second event here, the federal government, whenever I say HUD, you can just understand the federal government. So the federal government said, we are willing to provide 124 million to California to assist homeowners who lost their homes. So this is what the federal government proposed, but this needs to be approved by Congress. So it took a while for Congress to approve, and once Congress approves, then the state must design a plan, an action plan, or how they're going to use that money. And after the state develops that plan, it must be approved again by HUD. So this plan was approved in 2019 in March, about a year. So here we have 1.4 years, more or less, a year and 4 months. However, when HUD designed their state action plan, they actually re-estimated how much money they would need. And their estimated was that the California would need about $2 billion in order to rebuild from those fires. But the federal government only appropriated 124 million. So they have this big gap between what they needed and what they got. So they had to launch a survey. So they launched a survey in November 2019 to better understand the needs of the homeowners and to figure out the best use of this 124 million. So the first dollars that were appropriated in April 2018 from the fires in 2017, the first dollars that an individual received from these programs was in April 2020. So we're talking about 2 years between these two things here. So when we think about the housing recovery, there's a lot of discussions more recently in the LA fires on how the government is trying to get everything rebuilt in a few months. As you can see here, like 2 years after this wildfires in 2017, they haven't even decided who needed what. So why does this take so long? So one of the reasons for this is that early on here, when the federal government needs to define how much assistance it needs to provide, it doesn't have a lot of good data. It has basics of that. It doesn't have enough time to evaluate how much money the state may need. Because of that, they made some educated guesses, and that's why there's usually this big gap between these two what the state decides it needs and what's provided. And also this gap here at the beginning is also because the government is waiting this 4 months here to figure out what happened in the disaster and how much funding is coming from other sources. So there's a lot of waiting in this process here, waiting for data. And even waiting for data, the decisions we make are not good. We underestimate a lot of the times how things go. So for this study, after looking at this timeline here, I was wondering, could we better estimate how much funds would be needed by a state without this delay between when the events happen and the appropriation happens, by looking at previous disasters and looking at what happens there and trying to create models to simulate what happens in other disasters and what is happening in the current disaster and do a better estimate of that. So for this work, I used a combination of field data and agent-based simulations. So there's a lot of field data that was collected by different agencies that manage the post-fire recovery. I also used some data-driven approaches to gather some data from SBA and FEMA, which are providers of funding in the US. And I used this combination of models to simulate what would be the estimated amount of funding for California following these fires very early in the disaster period. So here are some of the results. So the histograms are results from simulations, and the dashed red lines here are the empirical data, what actually happened. So as you can see here, the simulation models are pretty decent at estimating how much funding California would have needed back there. The difference there is that these simulations could have been run maybe within a week of the disasters, and we would have this decent estimates here of how much funding was coming from different sources. And then the federal government would be able to make that allocation much better. So we argue that if we had these models at the time, we could have cut that timeline for this money to be disbursed by about a year. Or even actually more than a year and 4 months here, because we wouldn't need this survey, because we have a better allocation of funding, and because we wouldn't have to be waiting to get this data for this initial allocation here. So we would allocate a better amount of money to begin with. So this is just another example of how we can start thinking about using this computational simulations to reduce disaster risk. So just in the interest of time, I'm just going to get to my last example here, try to go a little quick through it. So this is an example of a very recent study that I was looking at how can we use computational simulations to understand the post-disaster risk in Canada now. So as many of you may know, Canada is a seismic place with some significant seismic risk. Some of you may not know is that, yes, British Columbia is the place where we have the highest potential impacts, but Quebec and Ontario are not far from it. So there is significant risk in Quebec and Ontario as well. So if I ask you, how would you finance repairs if your home got destroyed by an earthquake? So in Canada, if you have insurance, you're good. But if you don't, you're on your own, because the federal assistance does not provide funds if you for perils that are insurable. And because earthquake is an insurable peril, so you cannot count on the federal government for assistance. So you have to rely on your own savings, or you go to a bank and get a loan. So in this study, I was investigating what if we had some different alternatives for that. So, but because I wanted to do that, I needed to first create what is the baseline scenario? What's the baseline risk? So for this scenario, I worked specifically with the impacts of a potential magnitude 7 earthquake that had epicenter in the Strait of Georgia and I was looking at the impacts in this region of the country here. So I used some data from the OpenDRR, the Open Disaster Risk Reduction Platform for Canada. So I used their scenario analysis and some probability theory here to create 1,000 realizations of this, or to recreate 1,000 realizations of this damage, potential damage maps from this scenario analysis they have on their website, and to estimate the potential losses that would occur from these earthquakes. So there's a lot of uncertainty because some earthquakes can be more damaging than others. And then I look into what will be the unmet needs. So the difference between the damage to homes minus the damage that will be available from, let's say, insurance, and investigate what would be that gap. And I did some simulations with some what if scenarios. For example, what if Canada actually implemented an affordable insurance program, or if Canada had a low interest loan program like the one we have in the US. So just walking through here some of the results from that analysis. First, I investigated what if Canada had that low interest program? What should be the interest rate that that program should use? So to determine what that interest rate should be, I looked into the difference between the reduction in unmet needs versus the loss, because the market rates for loans, at least SBA in the US considers that a market rate is 8%. So if we are offering loans at any margin that is lower than that, we're potentially losing some money, but we're gaining some benefits from the fact that more people are going to be able to repair their homes. So there is a lot of analysis behind this here, but the key aspect here is that a loan program with about 3.5% interest rate would basically be cost-benefit neutral for Canada based on this analysis that I did here. So this analysis is more like a proof of concept than there needs to be more investigations to determine whether or not that 3% is the correct value. But this 3.5% makes a lot of sense because in the US, the Small Business Administrations provides loans of 4% interest rates, and it has been working for them for a long while. So here's an example of how we could use modeling and simulation to determine what is a viable low interest program in Canada. The second alternative I look into is like, what if Canada just copied New Zealand and created an insurance program the same way New Zealand has? New Zealand has here's some characteristics of that, the insurance program that New Zealand has. But basically what New Zealand does is they collect premiums every year from people, and every year there is no earthquake in New Zealand, they put that money aside so that whenever there is a big disaster, they have a lot of cash there. So they expect to collect about 130 million per year from that from their natural disaster fund that is funded by this affordable insurance program. So I was using some of this modeling as well to question, like, so how much would you need to charge from that insurance? What should be the premium in that insurance for us to have a viable program that would allow us to build a disaster fund that would help us if a large earthquake happens in Canada. So there are two things here that I'm going to walk you through briefly, is that if we implemented the same premium as New Zealand, which is 16 cents per $100 of insurance value, in about 3 years of capitalization, we would have enough funds to cover the expected costs of a magnitude 7 earthquake. This is assuming everyone will be on board with this, which is kind of optimistic, and also assuming that all the premiums that are collected and not used are being put towards this disaster fund. But And or we could try quite heavier premium of 50 cents per $100 insured, which would be equivalent of every year collecting the amount of money that would be the equivalent to the expected costs from this magnitude 7 earthquake. So my goals of this analysis are never to say what we have to do, because there's a lot of politics that will be involved in a decision like this, but to provide some information. So can we can you save the world with computational simulations? No. But can we help inform those one-shot decisions? I think that definitely yes. So my goal is that we have our current state of the world, and we can use these computational simulations to at least investigate what the potential futures are and navigate some of that decision making of what can we actually do to mitigate this risk. So with that, I will finish here, and I'll take any questions that you may have for the students that might be interested in this area. I'm still considering students for the next academic year, so you can reach out to me if you have a passion for these topics.